Welcome back. We just talked about vector product. In vector product, we are crossing two vectors. The result of a vector product is a vector, and therefore you realize moment is a vector. So if you want to calculate moment vector, you are dealing with two vectors, force vector and a position vector. You cross the position vector with the force vector to get the moment vector. That's what we have done. Now we want to talk about taking two vectors and dotting them. In other words, we are trying to find the scalar product of two vectors. All right? So as the name implies, the result of a scalar product is a scalar, meaning it is not a vector, it is just a magnitude, it is just a number. Now, obviously the question comes in, what is the implication or practical application of a scalar product? You already know vector product means moment in the context of engineering. So that's a real application of vector product. What is the real application of a scalar product? Well, it turns out you all kind of know what a scalar product is. In fact, in some ways, you have been using the scalar product without naming it, as I'm going to show you in a few minutes. But effectively, it is useful in finding the angle between two vectors. So for example, if you have two vectors, say x-axis, y-axis, ij vectors, what is the angle between them? 90 degrees. You know that, all right? But you can figure that out using a dot product. For example, you take your unit vector I, dot with j, you will get 90 degrees. I'm going to show you that in a few minutes. So what is the application of a scalar product? It is finding the angle between two vectors or finding the projection of one vector onto another axis, all right? So scalar product is very useful for these applications in engineering, and I'm going to show you that with an example. All right, let's do it. Let's talk about dot product. You know what a vector product is. Vector product is also known as cross product, and the result of a vector or a cross product is a vector. Now we are going to talk about scalar product. Scalar product is also known as dot product. Okay, the word dot. And it is indicated by a dot. For example, if we have vector P and vector Q, we dot these two vectors. Vector P dot vector Q, and the result is a scalar. That's why it's called a scalar product. And therefore, it is going to be equal to, by definition, magnitude of P, magnitude of Q. And earlier we had the angle sine angle, and in this case, that's Q. And we are going to have cosine theta. So if I have vector P and vector Q here, this angle is theta. The resulting value or magnitude is magnitude of these vectors times the angle between them, cosine angle between them. This is the definition of a scalar product. Now, obviously, this is what you learned in math, and our objective is finding the application of scalar product. So let's do this way. First, let's write vector P in Cartesian vector form. Px I, Py j plus Pzk. And I'm going to do this only one time, so we understand how we develop this expression for scalar product. We won't do this again and again, all right? Vector Q can be written as x component of Q, y component of Q along xyz axis, all right? So if I dot these, what that means is I'm going to take this expression Px I, Pyj, Pzk dot, notice that, Qxi, Qyj plus Qzk. I apologize for my handwriting, but I hope you understand what I'm doing, and I would suggest you should do this yourself instead of just copying what I'm doing. So I am going to do the FOIL. That means I take this Px, Qx, I dot I. I hope you understand what I just now did. So I took this, dotted with this, and I got I dot I. Now think about it. I is a vector and I'm dotting I. So it's like I dot I, and by definition, you know it's going to be the magnitude of I, which is 1, right? Which is 1. Magnitude of I again, which is 1. So it doesn't matter, I times cosine theta. What's the angle between I and I? It is going to be 0. So it's going to be cosine 0. And you know cosine 0 is 1, which is, right? So the resulting answer or magnitude I dot I is 1. Now think about it, what will happen? I dot j. I dot j, the angle between them is 90 degree. Magnitudes are 1, so I dot j will give you 0 because it is going to be cosine 90. Similarly, j dot I would give you 0 as well. On the other hand, j dot j will give you 1. So if you keep this in mind, in fact, I would recommend you to write down all that. What is I dot I, j dot j, k dot k? Those are all 1s and everything else is 0. And if you did that, if you expand this, let's see what happens if you expand this. Now I expanded px, qx, I dot I, and then I take pxi, I dot with qyj. So what will happen is, and I can keep on going this way, but what will happen to this will be px, qy, I dot j. And as I told you, what is I dot j? It is going to be 0. So if you expand this whole expression, which will have several terms, I believe it will have 9 terms, right? Most of the terms will turn to 0, leaving only the terms that will have terms such as I dot I, j dot j, and k dot k. So what you will end up having is px qx plus py qy plus pz qz. I suggest you try this out yourself. Okay? So here is the result of a dot product. And you know by definition this dot product is equal to P, which is magnitude of Q, and cosine theta. So if I have this PQ cosine theta is equal to Px Qx plus Py Qy plus Qz Pz Qz, look at this expression. I know my handwriting is not good, but I hope you follow. Magnitude of P, magnitude of Q, cosine theta, and then all the components of P and Q. In reality, if you are dealing with two forces, for example, or two vectors, it doesn't have to be forces, it could be position vectors, force vectors, or for that matter, anything. We know the XYZ components. If you know the XYZ components and the magnitude of them, we can find the angle, or we can find anything missing. In other words, scalar product gives the result as a scalar, and it is useful mathematically in finding the angles. So the application in engineering is finding angle between two vectors. Typically, if you look at the transmission towers or big cranes, things like that, you may have three-dimensional forces and they are way up there, 100 feet high. Or you can look at a crane that is used in building skyscrapers. And you want to find some angles, but you do know the direction of forces. Now, instead of going and trying to measure them, which is kind of risky and inconvenient, you can actually use the dot product. So the dot product is very useful in finding the angle between vectors. All right? That's a nice example. So if you understand scalar product, let's move on to solving a problem to find the angles. All right? All right. We are going to solve a real problem, finding the angle between two vectors using scalar product. Now, if you recall, in scalar product, let's say if I have two vectors P and Q, and if I dot them, you can represent the result using their components, Px, Qx, plus py qy plus pz qz. And you also know this result is equal to magnitude of p times magnitude of q times cosine theta. So if I rewrite this, look at this expression. If I rewrite this, if I have two vectors, I can say cosine theta is equal to px qx plus py qy plus pz qz divided by pq. All right? So if I ever want to find the angle between two vectors, I need the magnitude of two vectors and the components of two vectors. Then I can actually find the cosine angle, or I can find the angle using the cosine inverse of this expression. All right? Now, if you see this, I have a nice problem here that you see in your everyday life. Here, we have a volleyball net. Take a look at the volleyball net. It is supported, this pole is supported by three cables, all right? Cable AB, cable AC, cable AD. So in this particular case, we want to determine the angle formed by the wires AB and AC. So AB is here, AC is here. We want to find the angle between them, which means I need vector AB and vector AC, right? So A to B, here is my vector AB. A to C, here is my vector AC. So I need to find the two vectors. So I get these vectors, and then all I have to do is to dot AB with AC. And how do I dot it? You just now saw the expression. I need the x, y, z components of each of these and find the products and sum them up, right? And divide by the magnitude of this. So that's the problem I want to solve. And if you understand the problem, I got to create vector AB and AC, in which case I need the coordinates of A, B, and C. All right? Let me take a new slide or sheet here, which is kind of zoomed. So hopefully you can see that better. So here is my point A, and A's coordinate are, remember this is my origin, x, y, z. So A has no x component, which is 0, and it has positive 8 and no z component. I think you can see that coordinate of A. Let's find the coordinate of B. Coordinate of B is x component is going in the negative x direction, which is 6.5. So it's negative 6.5, comma. Y component is 0 because it is on this plane. And the z component is a little bit this way, so it's going to be 2. And then the component or coordinates of point C, x component is 0, as you can see, there is no x component. Y component is 0, and the z component is 6. I'm positive you can easily figure this out. This is 0, 0, 6. All right, we have all these components. So what is going to be vector AB? Well, it's going to be, this is your vector. I can draw a picture like that. AB, and I can actually subtract B minus A. So B is negative 6.5 minus 0. So negative 6.5 I. 0 minus 8. So minus 8J. All right. Plus 2K. I hope you understand how I got that one. This is from previous material. Given two coordinates, I want to find out the distance vector or the position vector. That's what I have done here. So this is vector AB. Make sure you note that as a vector. Then I have to do vector AC. So it's C minus A. Vector AC. So 0 minus 0, 0I, 0 minus 8 should give you minus 8J. I hope you see that. 6 minus 0 should give you 6k. All right? So now I have two vectors, AB and AC, and all I have to do is to dot them. AB dot AC, and when you dot that, that would be equal to magnitude of AB times magnitude of AC times cosine theta. The question is find this angle theta. So we have to find this, but we can actually find out the magnitude of AB, because magnitude of AB is equal to negative 6.5 square, plus minus 8 square plus 2 square and the square root, right? You know how to find the magnitude of AB, and that should be, if you did that, would be equal to 10.5. Remember, this is negative 5 inside. So that's the magnitude of AB, length of AB in other words. Similarly, you will have to calculate the length of AC, which would be is equal to 0 square minus 8 square plus 6 square, right? 0 square minus 8 square plus 6 square. And if you did that, you will easily see that's equal to 10. So we have the magnitude of that, and all we have to do is to do one more step to calculate the angle between them, and I'm going to do that on another sheet of paper. Okay. I have an extra sheet of paper here. Let's take a look at it. I'm going to rewrite some of these. Magnitude of AB equal to 10.5. Magnitude of AC is equal to 10. All right? And I have vector AB written as negative 6.5i minus 8j plus 2k. And vector AC is 0i minus 8j plus 6k. All right, sorry about rewriting all of it. So you have this. So now AB dot AC equal to magnitude of AB, actually it's 10.5, magnitude of AB times magnitude of AC times cosine theta, which I want to find out, equal to, you actually now do the PXQY combination. So you'll write minus 6.5 times 0 plus minus 8 times minus 8 plus 2 times 6. You can evaluate that. So cosine theta equal to minus 6.5 times 0 plus minus 8 times minus 8 plus 2 times 6 divided by 10.5 times 10. Simple to evaluate. From here you can calculate the cosine inverse of that, and if you did that, you will find theta is equal to roughly, I believe, 43 degrees. So that's the angle. If you go back to our original problem, we want to find this angle. And imagine if you don't want to do dot product, you got to go there, figure out the plane, and stick a protractor to find that. And imagine that is 100 feet high. It's very difficult to do it. So that's why dot product is a convenient way to calculate angle between two vectors. In this particular case, two force vectors. And we did this in a simple, easy way. All right? Hopefully you understand what I have done, and you may want to practice this in a couple of problems in calculating. The procedure is very simple and straightforward. Hopefully you understand this. Thank you.